So last time we talked about scaling in the context of droplets and bubbles, which is an example that I like. And so I showed you how to use this method of scaling to sort of get an idea of what's going on in this particular case. And today I'm going to try to zoom out a little bit and see how these methods can be used in other contexts. And so I'm going to try to give you some tools on how to use this method for the problems that you're into. And before I get into the presentation itself, I would like to tell you a little story, which is, I think, a good. We tried with Vivek and Mathieu to find the roots of these methods of scaling in the history of science, and we sort of came back to Archimedes again, which I mentioned last time, but through a different, for a different example, which is that so Archimedes was faced with the following problem. So you have a lot of stories about Archimedes. It's probably not the one that you're most familiar with. The problem that he had was this: he had a room with a complicated layout, and he asked how do you measure the area of this room? And the thing is that it's not a square, it's not a triangle, it's not any simple shape that you would have a formula for. And so he asked, what do you do when you're faced with such a situation? So anyone, what would you do? Huh? Drop it in water, and then what? So that's, you're not trying to measure a volume in this particular context. I mean, it's sort of connected to what you're saying. You're not trying to measure a volume. You're trying really to measure the area, like you have a room and it just has weird walls. So the thing is that there are two main methods that Archimedes laid out for this problem. The first one, which is the most popular one today, in particular with computers, is that you cut the room in two pieces. So for instance, you tile a room with simple shapes. Here it's a rectangle, so you know how to compute the area of the rectangle, and you just add up the area and you get to the answer. And of course, the more pieces you add next to the boundaries, the better the approximation. That's a very popular method, and it underlines basically calculus and differential calculus. But Archimedes also gave a different answer. He said, well, you can think about the fact that the room is can be filled with a liquid. So you can pour water into the room. You know the volume that you're pouring it into the room, and then you measure the height of the water, and then the area is just the volume that is your input, the volume you know, how much you put into the room, divided by the height, which is a simple measurement. And so you see, if you contrast those two methods, that you have very different outlook on the same problem. So the question was, what is the area of the room? The first answer is sort of rigorous in the sense that like it follows just the template. What you're asking for is an area. What you're going to use to answer the question are other areas. And you see that the structure is that you're adding. And if you think a little bit, you can also sort of do the same thing but backwards. So let's say the room is included into a house, and the house has a simple outline. You can then say, well, the area of the room is the square area of the house, and then you minus the tiling that you do from outside. So this way, you can understand that this first method, the sort of differential calculus method, the calculus method, gives you the answer in terms of adding and subtracting. And it doesn't introduce anything else beyond sort of the element that were in the question itself. You're asking about an area, you use areas. The second method that Archimedes introduced is different, because the second method sort of embeds this area into a larger space. So instead of just using the 2 dimensions of the plane, you also use the 3 dimension of a volume. You put it into it, and then you get your answer. So the scaling approach is more similar to the second approach to getting the area, which is that you're going to use dimensions that are beyond the question that you've been asked. If you remember, for instance, last time the framework was we were measuring a length versus a time, and then we sort of invoked stuff that were coming from mechanics, like the surface tension, the densities, things that had apparently nothing to do with the plane that we were measuring things, but that ended up being very useful. So in this particular case, it's fairly straightforward. So you're looking for an area. No, it's the other way around. You're looking for an area, and what you do is that you say, well, I'm going to use a volume, so the cube of a length, and divide it by a length, and I get an area. But the thing is that Archimedes realized even then that this could be sort of generalized. And so instead of just using a volume and a length to get an area, what you can say is that you can say, well, I have an area, that's what I want, and I can divide any quantity, Q1 and Q2, and as long as the dimensions that I get in the end are those of an area, this is a valid reasoning from a dimensional perspective. So I have a sort of an example here where you have your area and it's a room and you're renting that room. And the thing is that you know that you're paying $800 per month, and you know for weird reasons that it's $2 per month per square feet. And if you have those two pieces of information, these are your Q1 and Q2 in this situation, then the area that you get is just the ratio of those two quantities. And in this particular context, it's sort of close enough to normal life that we're not really shocked by it. But if you think about it, I mean, it's a very convoluted way of writing what an area is. An area is in square feet. And here you're writing it in dollar per month divided by dollar per month per square feet. I mean, it's a chain of units or dimensions, which is a little weird. In this case, you get the answer right, so you get the actual area of the room if you did not get screwed up in the process. So if those numbers were the actual numbers, so if you're not paying too much, for instance, and the actual area of your room is smaller. So the thing is, if you want to use this method, of course you need units and you need underlying dimensions behind these units that are robust and that people agree on. In the case of dollars or pounds, it's not really yet the case. So the word pound, 1 pound like the money and 1 pound for the mass, those two things have the same origins. That's why the name is the same. But those two units or those two dimensions took two different paths. On one side, the path of the mass, the idea is to have an agreement between people and make sure that if you use 1 pound here, it's the same over there. I mean, it took centuries to actually be implemented because people try to screw each other, basically. But the other side hasn't been standardized. So the other side, you know, if you have units and you try to, there could be two reasons for this, right? You could be, the idea is to make sure that the communication is happening, you know, in an honest manner. And in that case, I would say that's the path of the mass. And if you instead want to sort of take advantage of other people, then it's the other path. So if you think back again about the area, the first method, the dimensions of all of the terms of the equation, the area that we were looking for, and the area of all of the tiles that we were using in the process of solving the problem, all have the same dimension as the dimension of an area. In the second method, what you can use really is anything that will get you an area when you divide one by the other. So in the case from before, we were using square feet, and you had the price that you're paying per month, and then there was the price that was paid per square feet and per month. So the essential is that you can have some dimension of length to the power x, but then what you get here, so x being the power for this quantity Q2, this is going to disappear, and any other dimension, as long as they are the same, are also going to disappear. So that's for the case where you're looking for an area, but more generally, you can be looking for any sort of thing. So I don't know if you remember, but previously we started with a power law that was the radius of the neck in the case of a pinching water droplet, was going as k times t to the power 2/3. And then this k had these weird dimensions, which were L t minus 2/3. You can have weird dimensions of any kind. If they are combining length and time, you could put them here, and then you can write them up in terms of quantities, Q1 and Q2, which involve extra dimensions. So then, like, sort of the discipline that the field, if you want, that you're going to be finding yourself in is going to depend on the types of dimensions that you allow to be here and here. So in everything that I talked about last time, the things that we allowed here were kinematic dimensions, so some combination of length and time. And the extra dimension that we sort of used was the dimension of mass. But you can do dollars per square feet or whatever. It depends on what you're interested in. So that's what I was just saying. The last time we used quantities, the stuff that we were measuring were kinematic. So they were a combination of space and time. And the stuff that we used to explain those quantities were mechanical in the sense that they use the dimension of mass. We saw a few examples. The first one was the ratio of surface tension. So surface tension is this gamma here, and rho is the density. And what we had was the ratio of these two, and what we ended up was a kinematic quantity that just did not depend on mass. Another example that we saw after that was the ratio between surface tension and viscosity. And we also got something that did not depend on mass, that was a speed in this case, easier to understand. And then at the end, I did, but a little maybe too fast, so we'll come back to this. So this example, which is sort of classical, which is that you can think of a volume as a ratio between a mass and a density. And then I show another famous example, which is that you can think of an acceleration as a ratio between a force and a mass. So the common point between all of those dimensional equations is that the terms in the ratios, they all have the same sort of structure. And this structure is that they are all linear in the mass dimension, and they have some combination of length and time. And because of this, and this is what we said at the end last time, was because of this particular structure, you can think of any mechanical quantity of this sort as being on a plane with coordinates x, y, and y, x and y. Basically, I here are being if you have multiple quantities like this. So this is what I will call mechanical quantities, but they are mechanical quantities of a particular kind, which is they all share this structure. You could think also about mechanical quantities that have different exponents of the mass, and maybe I'll have time at the end to come back to this. So these are the mechanical quantities, and we saw 3 of them so far. We saw the density, which is a mass per unit volume, so 1, 2, 3, density. The symbol that I will use is rho. And then we saw surface tension. And then we saw viscosity. So I gave you last time this little piece of paper. Did anyone try to think about other places on this table, and what are the things that you might know that we might all know that would be on this table? Yes. So where would be pressure? Here. So I'm going to use sigma for this. So Pressure, nice. What else? Force. All of the major league players. Energy. Power. Huh? Where is momentum? Capital, lowercase. Uh-huh. Yes. Yes. So 1D density, if you want, but also since this morning with where is Gareth? Since this morning, there is another quantity that has these dimensions. So this morning, Gareth talked about normal stresses, and he said that a normal stress, which has the same units as a pressure, is often written, you can write it up as stress is equal to shear rate, which is the inverse of a time square, multiplied by a coefficient. I think Gareth used psi, yeah? Since I'm using it for another one, I'm going to use psi like this. So the normal stress coefficient is also here. So you see, and we saw this also with pressure. So pressure and stress, they have the same dimensions. And then you said surface tension and stiffness. The stiffness of a spring, for instance. The stiffness of a spring, if you think about Hooke's law, for instance, the force of the spring is the spring constant, which is usually called K, but I'm calling it gamma, times a length. So you can go from a stiffness to a force by multiplying by a length. So you can do this, and you can sort of fill the blanks. And if you do that, you can get to a map that looks like this. And the thing is that there are still a bunch of blank spots. And the blank spots are here because, after some time, Vivek and Mathieu and I, we just were tired of looking in the literature at various names that people gave. But basically, like, some people in some field might know that this quantity has a technical name, and you could put it there. So it's a sort of a table that is still in development. But the important thing is that you see that you have a bunch of different names. So for the stress, for instance, you can have the pressure, but you can also think about it as an energy density. And we saw that a lot in Peter's lectures and in George's lectures. We saw, for instance, that you had a lot of situations where you had a stress that was written as kBt divided by some length cube. So that's a case where kBt is an energy, and you divide it by a volume and you get a pressure. But you can also think about the pressure that you would get. So if you're into rheology, you would say, well, I also know that if you multiply viscosity by a shear rate, so if you multiply viscosity by the inverse of a time, then you get a stress. So you can think about all of these quantities in this table as being connected to one another through their dimensions. And so the thing is that once you have this sort of map, you can think about the interactions, so to speak, between various members of this table. And the thing is that the members of this table give you, last time I said with quotes like, if we know the physics of the situation, then we know that we have gamma and rho and this and that. The physics of any situation, usually the main players, the ones that are mostly used in research, you can find in this table. And the thing is that the various situations that you're going to encounter are depending on which one are going to be dominant in a particular case. But again, I want to stress that this is really, the table is sort of, it has no bounds. Here I had to stop at 3 and -5 because there was nothing I could find that was beyond this, but really there is no reason to stop. And so, for instance, I noted two cases in the lectures that we've had. George, for instance, talked about van der Waals, and in van der Waals you had those energies, which you have those potentials, and you have, I mean, you could even have like r to the power 12 in some cases, but here the case that George talked about was r to the power 6. So it means that the quantity c here is, if you divide this quantity by a length to the power 6, you get an energy. And so it means that if I didn't make any mistake, 1, 2, 3, 4, 5, I made a mistake. It should be here. So, and there are also quantities. All of these quantities have fairly standard names, even though they can have multiple names. But there is one that we felt was interesting to sort of define in a general sense with Vivek and Mathieu, is the strength. But we saw also an example. So when Peter talked about the bending modulus of a polymer, he said that the bending modulus was the kBt times the persistent length. So it was an energy times a length. And so it would be in this category. In some cases of solid mechanics, it's also called flexural rigidity. But we called it the strength because it's also used when you're comparing the strength of various fundamental forces. People say, well, you have h bar c. So h bar is an action, so it would be here. And if you multiply an action by a speed, it means that you're multiplying by a length and dividing by a time. So h bar times c is a strength. And you also have another example of strength, which is E square 4 pi epsilon 0. So here, it's good that it's right here. Here I have a stress, and it's an energy, a thermal energy divided by a volume. But you see it involves the temperature, and the temperature is not really originally part of this whole scheme, because this scheme doesn't involve the dimension of temperature explicitly. But people have found at the end of the 19th century, people have found ways to connect thermodynamics to mechanics. In the case of thermodynamics, the connection is done by the Boltzmann constant, which is used as a translation constant between a temperature and an energy. And you also have, in the case of electromagnetism, you have this constant, or one over this constant is also called the Coulomb constant. And it's a translation factor between charge, which is also a dimension that is not really part of this map, and mechanics. So if you look at the dimension of this term, which is very important, of course, for electrostatic interactions, this has the same dimension as these combination. So that being said, I want to talk to you now about how do you combine just pairs of these quantities. That's how we started last time, also talking about duos. We talked about one case in particular at first, which was surface tension and density. And I want to tell you how to generalize this, because if you think about the map that I was giving you before with the grid and the mechanical quantities, there was about 20 or so mechanical quantities. If you think about all of the pairs that you can make from all of those quantities, that's a lot of pairs. So instead of going through them one by one, I want to give you a little, like basically how the template on how to do this, and then we'll go over a few examples. So the template is very simple. It's the same formula that we had before from Archimedes' example, except that it's in a particular case where what you're looking for is a kinematic quantity, and what you're allowing on the left-hand side are mechanical quantities. So it's very simple, is that if you start with quantities, each time I use the symbol Q, it means like any quantity that is in the table over there. And so if you have a quantity like this, you know that it has a dimension of mass and some combinations of the dimension of space and time. So Q1 here would have dimension M Lx1 and T y1, and Q2 would have dimension M Lx2 Ty2. If you divide one by the other, the dimension of mass is going to disappear. And what you're going to end up with is just purely space and time dependent. And that's really it. I mean, this formula, then you can twist and turn this formula in a bunch of different ways, which is what we're going to do. But that's really the core of this of connection between what's going on in this sort of table of mechanical players and what you would observe in terms of kinematics. So again, we saw one example which is sort of super basic. In that case, you have mass, you divide it by mass per volume, and you get a volume. Another case, but which had to wait sort of 2,000 years between Archimedes and Newton, is if you divide a force by a mass, you get an acceleration. So before I get into this kind of case where the output that you get is fully kinematic, it depends on both space and time, I'm going to talk to you about a few cases which are just involving space first or just involving time. So I have a list, and then this is supposed to stay on the board for a while we talk about what's there. So if you go back, so if you have a quantity Q1 and it has dimension m Lx1 Ty1, and then you have a quantity Q2 which has dimension m Lx2 Ty2. In the special case that those two quantities have the same time exponent, which means in terms of the table over there, it means that they are on the same line. So if they are on the same line, it means that y1 is equal to y2. And then if you take the ratio, what you get is, so let's call that y. The mass goes out and the time dimension goes out, and so what you get is Lx1 minus x2. So if you think about any two quantities that are on the same line, so for instance we talked about energy and stress, if you divide an energy by a stress, what you're going to get is a volume. If you divide an energy by a force, what you're going to get is a length. If you divide energy by a surface tension, you get an area. So basically, take any two quantities that are on the same line. If you divide them, what you will end up is purely spatial. It could be a length, it could be an area, it could be a volume, or it could even be something more complicated. So for instance, here, you have a force density. So in aerodynamics, you find this a lot when you have rho times g. So if you have rho times g, rho is a mass per unit volume. You multiply it by an acceleration. What you're going to get is a force per unit volume. If you have a force per unit volume, it's 1, 2, 3 from the force. But if you divide an energy by a force density, what you're going to get is something that has L to the power 4. And you could say, well, that would be hard to interpret because I know what a length is, I know what an area is, and I know what a volume is, but I don't know what four-dimensional volume is. But as it turns out, this shows up in nature, and I'm going to give you one example of this. So the first example is the one that we were just talking about, which is that if you divide an energy by a stress, what you get is a length. So if you think, for instance, about the example that Peter was giving for a polymer, if you want to know what is the mesh size for your polymer, the mesh size for your polymer would be given by the thermal energy, which would take the place of E, and the stress is you could measure by some mechanical measurement. So I'm going to turn to you and ask you if you know some of these equations. So I gave the symbols And then the names here tell you what the symbols mean. So for instance, we saw this one at the beginning of the first lecture. So you have surface tension and force density. So which type of length is given by the square root of a surface tension and the force density? The force density is usually rho g. So what is this length? You remember? The capillary length. So if you remember in the first lecture, I gave you the case of, I said at the very beginning that it was a disclaimer, which was that everything that I was going to talk about was about small droplets, where the drops were smaller than the capillary length. And I said, well, the capillary length is sort of the threshold where surface tension, under this threshold for things that are smaller than this, surface tension is more dominant than gravity. And so if you have this case, it's the combination between surface tension and force density. Do you know any other from this list? So we know this one. This one is surface tension and elastic modulus, for instance. So this one is called the elastocapillary length. So in this case, I mean, it shows up in a bunch of different contexts, but one instance is that you have a drop and it's on an elastic substrate. So if it's on a completely rigid substrate, the drop is going to have some shape depending on the wettability. But if you have a soft substrate, the substrate is also going to deform. And so you're going to have a ridge, and this ridge, the length, the characteristic length of this ridge is going to be given by this ratio. Another one that I like is this one. So this one is, if you have if you think of a planet and you want to know what's the order of magnitude of for the size of this planet, what people usually do in this situation is that they use what they call the hydrostatic equilibrium. The reason why it's called the hydrostatic equilibrium is that it comes back to the definition of pressure from in the context of barometers. The idea is you say, well, the length here is some balance between the compressive force, if you want, of gravity and the elasticity of the material. So it's sort of, you have a pressure inside and you have the gravity that is pulling things inward, and the size that you end up with is sort of a balance between those two things. So in this particular case, you can think of the inward sort of force as a force per unit volume. That's rho g, or what I call psi. And then in the numerator is the pressure, so or the elastic modulus. So if you have a material that has a very high elastic modulus, it's going to be able to resist more the compression from gravity, and so its size would be larger. So all of this is to say that you can have a bunch of different examples of length scales that are built from mechanical factors. The most famous one, and the one that is so trivial that you don't really think about it in terms of a balance, is the one that comes from Archimedes. It's the balance between mass and density. So all of these are basically using the same idea. It's just that they are using different pairs of mechanical quantities, but they are built on the same idea. And the list is very long. Here are just a few examples. One maybe that I can talk about before moving on to the next thing is this one. So I said, well, if you divide an energy by a force density, what you get is a length to the power 4. And you could be like, oh, that's weird. Like, I don't want to think about this. But people did. And so, for instance, there is a whole literature on craters. So if you think about, for instance, you have an explosion that makes a crater in the ground, or you have an impact of an object on the ground, and it makes a crater. In that case, you have sort of the physics of the situation is the combination of two things. You have the energy of the impact, that could be the energy that is released by the explosion, or the kinetic energy of the projectile, let's call that E. And you have another factor, which is the force, like the weight density of the ground material. So the ground material that is being ejected, it has a weight, and if you think about it as a continuum medium with a sort of average density rho, then you have a weight per unit volume, rho g. And so if you combine these two things, you say, well, you have the energy, which is sort of driving, which is going to increase the size of your crater. And then you have the force density, which the larger it is, so the heavier the ground material, the smaller the crater. That's why it's in the numerator. And if you combine the two, you get the size of your crater. So basically, it is saying that even though if you just take the ratio between those two quantities, or any quantities that are far enough from one another, what you might get is a length that has a power that is apparently hard to interpret. If you take the appropriate root of the ratio, what you get is a length. And so in this case, for instance, you get the size of a crater by combining those two quantities. So if you are faced with a situation where you have an obvious characteristic length, it could be the size of the crater, it could be the size of a planet, it could be the size of the droplet before it falls down, it could be the ridge in the case of the wetting of a fluid on an elastic substrate. If you have a length scale, you observe it, you measure it, and the thing is that you can do another experiment, maybe use a different fluid, maybe throw the ball in the ground faster, or change the parameter of your situation, and then you can check how the result depends on this parameter. So for instance, if you're thinking of the crater, you take the same ground material, it's on the same planet, so the value of G is the same, the value of rho is the same, so the value of the denominator is the same, and then you just throw the ball faster, increase the kinetic energy, look at how the size of the crater depends on the kinetic energy, and if you see that this crater indeed depends as the power 1/4 of the kinetic energy, then you know that the other quantity must be a force density, and you can compare with the value of the force density that you can measure. So that's sort of the one sort of simple entry to how to use this table, is that you can use this table to construct any sort of length scale that you want, just by taking ratios of quantity that are on the same line. And then the type of ratio that you might take will depend on the type of quantities that you think are important in your situation. Another thing that you can do is sort of the reverse. Instead of taking ratios of quantities that are on the same line, you can take ratios of quantities that are on the same column. And in this particular case, what you will get is something that has to do with time rather than space. So we saw also some examples. I mean, this morning we talked a lot about, and in rheology in general, you can talk a lot about the ratio between viscosity and stress, which give you the relaxation time. But you can also talk about the ratio between, and Gareth mentioned this, that we often think of just viscosity as a material parameter, but right from the start, even in the simplest cases, you also have normal stress coefficients, and so you can also construct timescales by the ratio with the ratio between viscosity and normal stress coefficients. Of course, since viscosity is above stress, if you divide viscosity by a stress, you get a timescale. But then if you want to create a timescale built from your normal stress coefficients, you need to divide the normal stress coefficient by the viscosity, sorry. The thing is that in the simplest model that Gareth also mentioned this morning, the Maxwell model, the timescales that you get when you do this ratio or when you do this ratio, they are connected. There is just a factor, numerical factor between them. But in general, it's not the case. So that's a very important column for rheology. But you also have a super famous example, which is the ratio between mass and stiffness, which is giving you the period of oscillation for the spring and mass system. So that's this one. So this one is a time scale. If you think about the fact that usually, I mean, basically replace gamma here by k, which is usually the symbol that is used for stiffness in this situation, and then you get the period of oscillation for your spring and mass system. So that's a very super famous case. That's the rheological cases that were mentioned on several occasions already in the school. And then you have those two that I like also. You have energy and power. This one is useful if you think of, for instance, you have a car and you want to know how far you can drive with the car with the full tank. And so in this particular case, the power of the car is going to be P here. So if you have a very powerful car, so you're not going to be driving very far because you're going to use the energy very fast. So if you have, for instance, 70 horsepower, which is a small car, you can take 70 horsepower here. We can convert that into watt if you want. And then for the energy, you can think about the gas tank. So the gas tank is, I don't know, like I don't remember the figure for small cars, maybe 40 liters. You have 40 liters of fuel, and that fuel has a particular amount of energy per liter. You use this, and then you get in the end the value for how long you can drive with the car. But it's sort of a mundane example of use of this particular formula. But this formula works for any system that has a power, which is basically using energy at a given rate, and some source of energy. So in particular, you can use this one also if you want to know the lifetime of the sun. And there was a big debates about this because people knew what the power of the sun was because you can measure it just based on the luminosity of the sun. In astrophysics, luminosity is just another term for power. It's given in watts. For the sun, it's, I don't remember, like some huge number, 10 to 26 or 30 something. And then you want to know how long the sun is going to live. You need to know how much energy is at its disposition. Because you know at which rate it's burning up this energy, but you don't know what the energy is. And so at the beginning of the 20th century, there were a lot of debate as to what was the source of energy, and people tried different things. You can do it yourself. So if you think, for instance, of the sun as a big gas tank, like the car, with the same sort of fuel, you'll see that after a few thousand years, it's just stops. So then Kelvin, he did a bunch of great stuff, but in this particular case, he ridiculized himself. He thought that the energy, it ended up being very useful, so that's good. He thought that the energy was gravity, because people had not discovered nuclear energy. So he thought that it was just compression from gravity. So if you use the gravitational potential energy for the E here, what you get is a value of a few million years. And there was a big debate because the geologists back then had already measured a bunch of stuff like fossil records and everything, like, I don't know, geology stuff. And they were convinced that like the Earth was billions of years. And Kelvin was like, no, this is millions of years. And then eventually with the advent of nuclear, the progress that was made in terms of about nuclear physics, it was understood that the reason was that the energy is really nuclear. Another important one, especially for quantum mechanics, is this one. So action in hydrodynamics is not really used often, but it's all over the place if you do quantum mechanics, because in quantum mechanics, you always have h, or the Planck constant, or h bar. And the Planck constant, as I was saying earlier, is an action. And so as soon as you're dealing with quantum mechanics, usually one of your quantity of interest is going to be this Planck constant. And this one is, so if you think of h here, which is sort of the generic symbol that I use for action, think of h as h bar, and you divide h bar by an energy, and that's sort of the standard equation for quantum mechanics. It's usually written like this. Omega is the frequency, it's the inverse of a time. So if you put it on the other side, 1 over omega is equal to h bar divided by E. So that's an important example that involves the energy and the action. So for instance, we saw that on this column, that's super useful in rheology, and this column you find more in, I don't know, like quantum mechanics and stuff like that. You can think of the ratio of action and energy, of energy and power. You could also think, and you're invited to think about the ratio of action and power, but any ratio of quantities on the same column will give you a time scale. So again, if you're faced with a situation where you have a time scale, it's obvious, you see in your experiment that there is a time, and you want to explain it in terms of mechanical terms, well, you have a lot of choices. And the number of cases that you could use are going to be constrained just by the quantities that you think or other people think, other people before you in the same field had thought were important. There is one thing that you can do also now, which I'm giving you just a few examples, is that you can think of quantities. So we talked about two special cases, same line, same column. What you can do now is think about quantities that are on the same diagonal of slope -1. The reason to do this it seems sort of arbitrary when you frame it this way, but the reason is if you do that, what you get is a speed, and people like speeds because it's sort of the go-to kinematic quantity, and it's the sort of simplest way to combine length and time. And so you have a few examples. This one is the one that we talked about in the first lecture. It was the viscocapillary speed. It's the ratio between a surface tension and a viscosity, and it's on the same sort of. I mean, it's more recent. It has, you know, it did not emerge until the 20th century. People were not really into this, but it has the same sort of structure than another more ancient kind of speed, which is the ratio of a stress or a pressure and a density, which is the speed of sound. So here I give you a few examples, but I want to now move to the general case, which is take any pair of quantity on the table, what is it that you get? One example that is super famous is one that came back to Taylor and that you find in any textbook on dimensional analysis. Taylor was interested in for whatever reason, this one is slower. Oh, no, yeah. So Taylor was interested in the explosion, atomic explosion, and the kinetic. I mean, basically the physics of atomic explosion. What you see here are snapshots of the first nuclear test, that was Trinity in New Mexico in 1945, and the idea, you know, you remember the case of the pinching droplet, and the whole shape of the pinching droplet is fascinating. But then I said, well, we're going to focus on a sort of a simpler metric, which was just the size of the neck. Here, Taylor did the same sort of thing. He wasn't really interested in all of the details of the explosion front as it grows over time. He was saying, okay, let's look at it in terms of just the average radius of the ball as it grows. And so in this case, what Taylor did was to say, well, I'm going to look at this data. I'll show you the real data after. I'm going to look at this data, and in this case, what he saw was that the radius of the ball is growing as a power 2/5 of the time. Before we had 2/3 for the pinching droplet, and now it's 2/5. Why is it that in the case of pinching droplet we had 2/3, and here we had 2/5? Well, now you can see this graphically. So in the case of an explosion, the driving factor, what's driving this explosion, is the energy input. And what's slowing it down is the inertia. And so in this case, the two players, the two mechanical factors that are important are energy and density. And the thing is that energy, so you can now see the value here of the exponent as a consequence of the relative placement of those quantities, because you have, there are spaced by 2 in the time dimension, and then they are spaced by 5 in the length dimension. So if you remember the formula from earlier, which maybe is still written, if you take the ratio of those two quantities, then what you're going to get is something that is L to the power 5 divided by T to the power 2. And if you rewrite it in terms of a length versus a time, this is what you're going to get. So really the placement of your mechanical factors give you the scaling. So if you now say, well, I'm going to keep the same impeding factor, which is here the density, I'm going to keep the same one, but I'm going to look at a situation where the driver is not an energy, but it's a force. So that's another situation. And in that case, the power is going to be different. It's going to be 4, 1, 2, 3, 4 divided by 2. 2 divided by 4, which is going to be 1/2. So I'm not going to give you all of them, but I'm going to give you the one that you know. This was combining surface tension and density. And in this case, the power was 2/3. I'm not going to give you all of them, but basically, the big question that the big frustration from the first lecture was this whole what is the physics thing. What the hope is that with this table, the idea is that you can find you can better identify what the physics is just based on this sort of map. So you have a map and you have many sort of players that you can have. And by identifying those players, then you can sort of compute the kinematic consequence. It could be a length scale, it could be a time scale, or it could be just a regime in the general case. And you can compute those from the mechanics. What I want to do now, because I don't want to get lost with this, is to come back to where we left off last time. And last time we had a surface tension, and we had a viscosity, and we had a density. And what we saw was that if you combine surface tension and density, what you get is a 2/3 parallel. This was the first thing that we saw. Then if you combine surface tension and viscosity, what you get is a linear regime. And if you combine the three of them, you get the point of intersection. But then we had this weird extra regime, which was the late... Yes. Sorry, I'm jumping from slide to slide. Yes. So we had something that looked like this. So for instance, this is the curve that you would expect for the pinching of a water droplet. So you had the water droplet, and in this case, the real time is running from right to left because we've inverted. We've defined the time scale here, the variable time, as the duration that is left before pinch-off. So this curve should be familiar because we saw a bunch of them last time. In this particular case, what we observe is purely kinematic. So we observe a length and how it evolves with time. You know, in the lectures that we've seen so far, we also saw examples of scaling that are more complicated than this because, for instance, you can have a scaling on a flow curve. In the case of a flow curve, what you measure is a stress, and you look at how the stress is changing with respect to the shear rate. So in those cases, you could still use some of those methods, but not exactly in the same way because you don't start with the same sort of starting point, which is that you start with only kinematic quantities. So what we saw last time is that you can invoke the dimension of mass to explain what's going on those regimes. We saw viscosity and surface tension here, and we saw surface tension and density here. But then we had a regime here that was not mechanical at all. So it was, I said last time that it would be nice to try to understand if we can think about it in terms of a length scale, like for instance, the one that I showed you at the very beginning. So, one thing I added this because someone asked me this question. So, in real life, what you observe is not exactly just sharp regimes that are a straight line and then another straight line. In real life, you often observe transitions between those regimes. And so the thing that the framework that I'm talking to you about is really about the straight line approximations, but it cannot capture what's going on precisely near the transitions. Okay. My slides are not in the right order. Let's start again here. So that's where we left off. We have three mechanical parameters: the surface tension, the density, and the viscosity. And here, if you remember, you're representing the data in a particular system of units, which is sort of implied by the mechanical parameters, which is the system that was first used by Onsorg, where you use the point of intersection between the early viscous regime, viscocapillary regime, and the late inertial capillary regime. And then the color code gives you the value of the Onsorg number, which combine the surface tension, the density, the viscosity, and the size of the droplet or bubble, which is sort of the maximum size that you can reach. And we had two different cases. The case where the size that you can reach is above the crossover, which allows you to see this, or it is below the crossover, and you will never be able to see the two-third regime that we introduced first last time. And I said, I think, but maybe a little cryptically, that even if you know this area, this field of research, you might have been frustrated about the fact that I left out some aspects of what the experiment have seen in these situations. But I also said that if, even if you don't know anything about this field of research, maybe you can already be troubled by something with this plot, which is that we understand now that the important is that you have a number of players, and here we have three, which are given here. And then from those players, you can build various pairs that are going to give you various regimes. And here we have a trio of quantities, and I only showed you two pairs. So I showed you how surface tension and density combine and what it gives you. I showed you surface tension and viscosity, and that gives you the linear regime. But there is a third pair here, right? So who can tell me this? Right, exactly. So if you combine viscosity and density, you get another regime. And let me see if I have it on the slide or if I'm writing it on the board. If you take the ratio of the viscosity of the fluid and the density of the fluid, what you have, because now you have them on the board here, so I don't have to recall the dimensions. Viscosity has these dimensions, the mass cancel out, and what you get is an area per unit time. And so this quantity here is also called the kinematic, you were saying the kinematic viscosity, and it's involved in the diffusion of boundary layers. And the thing is that if you put it on the same plot, you find it here. So you can do that on your own because it's fun to do once and then to be convinced of this for the general case, is that if you have a trio of quantities that are on the table over there, and you compute the regimes that are associated with each pair of this trio, each regime, I mean, the three regimes are going to intersect at the same point. There is only one condition, is that the three quantities that you choose on the table should not be aligned. So if the three quantities that you choose, for instance, are on the same line, this will not be the case, and you can think about this case on your own. But as soon as the three quantities are not aligned, they're going to generate three lines, three power laws, and the power laws are going to intersect at the same point. So last time we derived the coordinates of the unstroked points, which depended on viscosity, density, and surface tension. We derived those coordinates by equating this regime and this regime. But you can do it on your own. You can also find the same coordinate by equating this regime and this regime, or this regime and this regime. So it works for any pair, which is just to say that they have the same intersection. The important thing, of course, here is that the d here, the variable d, is not the same as the one that we used before. So in this particular case, we had used d for one single purpose, which was to describe the neck of the drop when it was pinching, or the contact radius when it was coalescing or spreading. Here, it's not exactly this, because if you think of the situation where this scaling law comes up, it comes up in the case where you have a boundary layer. So if you have a plate, for instance, and you start moving that plate at t equals 0, the fluid far away from that plate is not going to start moving instantaneously. It's going to take a while for this fluid to be set in motion. And if you measure the size of the layer of fluid that is moving after a given time t, this is going to be given by this equation. In the case of the water droplets, you don't have like a plate that is moving like this. It's more complicated than this. But this scaling you find in situations also where the kinematics are a little bit different. So for instance, if you have a flow where the plate is not moving, but it's a uniform flow far away from that plate, and it's hitting the plate, the size of the region where the flow is being slowed down will also follow this scaling. So in the case of the droplets, I don't have the answer as to where exactly those boundary layers are, but the fact that those three regimes intersect probably tell you that if you think of the flow inside now, the droplets, not anymore just the radius of the neck, the properties like the geometry of this flow and what goes on inside this flow, whether the boundary layers are extensional or shear, are connected to the other two regimes. But I don't want to say more about this because I don't know anything about this. I want to tell you about one last thing for the remaining time, which is that I forgot, again, the scaling before was like, you remember before I included all of this, it was very nice because you only had two regimes, one and the other, and it had everything collapsed. And then I told you that I cheated you because I didn't include the late regimes, and then if you include the late regimes, the picture is not as beautiful. Well, I cheated you in another way, which is that I left out like practically half of the experiments in this field. So basically, there was a big confusion for a while as to why some experiments, for instance, would see the 2/3 regimes, and some experiments would see something completely different that I didn't talk about yet. And so that's what I want to talk about now. For instance, this experiment from Paulson, you see the coalescence of two saltwater droplets in silicone oil. And if you follow now the radius of contact between those drops, you'll see it doesn't follow at all the template that I've been building. So all of the other curves we saw last time, and these new data points is the experiment that I just showed you. And here it's just it's not following at all what we could expect from the power laws that we. So last time we had two power laws plus the weird late regimes that it was just like a geometric constraint. And now we have this. So we have a lot of holes in our model because we don't really have any mechanical understanding of this. It's just a purely geometric factor, constraint if you want. And now we have this new thing, which is like a completely different new path. So the thing is that I'm going to show you is that these two issues are actually connected and they can be resolved using the same idea. This regime, the one where that is really like not on what we talked about before, this is a 1/2 power law. So it's in this regime, the radius of contact between the two drops is growing like the square root of time. And it's actually the oldest probably of all of the regimes that I talked about drops. It dates back to Rayleigh. And Rayleigh wrote it in this way. So he said, well, you have surface tension, and you have density, and you have the size of the drop. And the radius of contact is going to be proportional to the time to the power 1/2 and this factor. But you see that this factor doesn't follow the template that we talked about. I mean, it has two mechanical factors, the surface tension and the density, but it also have this extra parameter, which is just geometric, which is this capital D, the size of the drop or bubble. The thing is that if this was just this case, this one experiment, then we could just say, well, but this particular regime has been seen on many, many occasions for pinching, for coalescence, and for spreading. So here I just added a bunch of data. I'm going to zoom in so you can see a little bit better. But you have a bunch of data that are on this plot that don't follow any of the lines that we've drawn so far. So if I zoom in a bit more, what you see is that you have a bunch of different lines of slope 1/2 with different prefactors. The prefactors, the value of the prefactors being set by this. Zooming in, you can see a lot of experiments, again, a bunch of different setup, but they are all following the same slope with different values of surface tension, density, and drop size. If you rewrite it in terms of the Onsorg units, because here what I'm plotting is not the actual size and the actual time, it's the size divided by the point of intersection and the time divided by the point of intersection. If you do this, what you end up with is that in terms of the Onsorg number, this regime is a power 1/2 that goes through the origin, but then that is shifted by this factor. So if you change the Onsorg number, you're going to get a bunch of different lines. And so that's why the color of the line reflects the position of the line. So it's a big mess. And if we go back to all of these equations, this is what we had, right? This was the nice starting point, that we had a pair of mechanical factors, and we could understand one as driving the dynamics, that was the surface tension, and we could understand one, the density, as sort of slowing things down. We put those two together, and we got this just by dimensional analysis. And then we did the same thing with surface tension and viscosity, and then we got the result from dimensional analysis. We also had this one for free. Just we didn't even think about it at first, but if we put one and one together, we saw that we had a third pair from the same trio. And then we had two weird stuff, is that we had a regime that was almost cheating, which was you have the final regime, which is the plateaus on all of those plots, and it was just given by the fact that the drop size was a given value, capital D, or the bubble size was a given value, and so that was the end. But we had no mechanical understanding of it. And then there is this new regime, which is really annoying because it's sort of using mechanical terms, but it's also using a geometrical parameter, and we don't really know how to what to do with it and how to deal with it. In technical terms, the first three equations are called self-similarity solution of the first kind. I mean, they were called by Barenblatt, who worked on this, and that's the term he used. And what he meant is that it's you can get to the solution just by using dimensional analysis. And then you have more complicated cases, self-similarity of the second kind, where you can say, well, I'm looking for a radius that is going to depend on the size of the droplet, the surface tension, and the density, and you'll never get the answer because you have too many parameters and you will not be able to constrain enough to find the answer. So what do we do? At this point, we could rewrite this in terms of the unsorted number, which we did a little bit before. So if you, if you try, you can do it yourself. If you try to find a solution to this equation, so you try to find a length scale that depends on those 4 parameters, the only thing that you'll be able to say is that the size of the neck divided by the final size will be some parallel of the time divided by the time of the inertial capillary time that I talked about last time. So it's a little disappointing. And at this point, we're supposed to be sad and complain about the limits of dimensional analysis. So usually at this point, you say, well, we've done well with the self-similarity of the first kind. So there is the first 2 regimes, and then the third one, if you include the kinematic viscosity. But now we reach a situation where it's really beyond the reach of dimensional analysis, and so we need to actually do solve the equations and do real work. But I don't want to do that. So the question that I asked before, and the answer is no, can this regime be obtained by dimensional analysis, just brute force? You'd say, well, I have a radius of contact or of the neck, and I want it to depend on these 4 quantities, and can I find the answer? The answer is no. I'm going to ask a slightly different question, and we'll see that what we hit here is not really the limitation of dimensional analysis in general. It's really our own problem. So the second question, the question that I'm asking now is, can this regime be written as a ratio of 2 mechanical quantities? So I have this equation, and I already know it. People told me you have this equation. Can I write this equation in the form Q1 divided by Q2 to some power times time to the power 1/2? So basically, can I rewrite this part such that it is a mechanical quantity on this table divided by another mechanical quantity on this table? And the answer is yes. I mean, you can do that actually in in multiple ways. But the simplest way is actually the most fruitful in this case, which is that you can say, well, I'm going to keep this as one of my mechanical factors. I'm going to say the density is still important. It's still what slows down the dynamics. But I'm going to group what I have in the numerator. I'm going to say, well, this is, you can write this as surface tension times the drop size or the max size. But I'm going to call this a force because it's a stiffness or a surface tension times a length. And so if you look at the table, this gives you a force. And you can think about it as sort of the whole capillary force on the whole droplet. And then if I do this, well, I've reached my goal, which was to write this equation, which was annoying us because it had this structure that was not fitting the mold. And I can write it in this way. I can write, okay, well, I have a force and I have a density, and that's it. If I start, basically, if you know too much, you don't get the answer. If you only know that you have a force and you have a density, then you get the answer. And the thing is that this doesn't stop here, because so before you had this 3 nice equation depending on 3 mechanical parameters, but then you had a geometric parameter. And the idea is that if you want everything to be sort of on the same playing field, you need to get rid of this geometric parameter and make it into a mechanical parameter. We've done this here by writing gamma d as F, a force, a whole force, a capillary force on the whole drop. But if f is equal to gamma d, it also means that d is equal to f divided by gamma. And so we have two regimes that were sort of annoying us before, which involved a geometry quantity, and now they are written in the same way as as the others. They are on the same sort of, they have the same structure. And the good thing and final thing is that we get something for free, which is that now we have 4 mechanical parameters. The first 3 that we worked with were these 3. And then by trying to figure out how to regularize, if you want, these 2 equations when they were written in terms of the geometric parameter, we introduce a force F. So now we have 4 mechanical parameters, and we have only 5 pairs. But from a set of 4, you can make 6 pairs. So which pair is missing from the list? So we have gamma and rho. So we have gamma and eta, gamma and rho, and gamma and f. So all of the pairs that involve gamma are here. We have eta and gamma, we said it, eta and rho. We don't have eta and f. So if you were not convinced that this little trick of turning the geometric parameter into a mechanical parameter was a good idea, here you get something which is that first you regularize the 2 that we had that were sort of not fitting the mold, and now we have a last one that turns out also to be very useful, which is that if you combine force and viscosity, so I think let's do this one. Let's help me do this one just to make sure that so force divided by viscosity. So M, L, I hear. And so we get so what type of regime? So if I write it like this now, what do we get? So d square, let's call it this. This was the dimensions. Without the dimension, and so if I now write this as a d of something, so it's going to be d right? And so if all of this makes sense, this should have some sort of relevance to the dynamics of droplets and bubbles. And luckily it does, because there is another type of dynamics that I had left out, which is also coming from experiment by Paulson. I mean, other people also saw this, but his experiments really show this beautifully. He looked at the coalescence of bubbles and droplets in viscous outer fluid. I mean, in outer fluid with different viscosities. And what he saw was, so he recorded the radius of the contact between the 2 drops for various values of unsorted numbers, depending on the viscosity of the outer fluid. And what he saw is that in the case where the unsorted number is smaller than 1, you have this regime, which is the one that we had sort of re-mechanized, which is Rayleigh's regime. And in the case where you have unsorted number greater than 1, you have a different regime, which depends on the force that we just built and the outer viscosity. And if I put these on the plot, I remove all of the other data points, otherwise it's just a big mess. But you see that if you put them on the plot, they don't follow at all the lines that we had drawn first. And if you add the data, it's worse. Now it's really a big mess. If you add all of those things, all of the experiments that show the Rayleigh regime, it's really becoming to be complicated even in these units. But now if you look back at those regimes, what we had before was this. So we had two cases. That was the end of last lecture. We had the case where the Unsorg number was greater than 1, where we had viscocapillary and then it stopped. And then we had the case where the Unsorg number was smaller than 1. It was viscocapillary, inertial capillary, and then it stopped. And now what we have are additional paths. So what we have is a path here, which is, you remember the experiment by Paulson for the coalescence of following Rayleigh's regime. We had all of those data points that were going through another route. Well, this is a new path that we have here. And we also have a new path for viscous outer fluid coalescence. And so the thing that is important is that all of those lines, they are now equivalent to one another. So all of those lines are connected to a pair from the same set of mechanical parameters. So the thing is that you have surface tension, you have viscosity, you have density, and you have the force that comes from the conservation of volume or the capillary force. And all of those lines, if you just draw them on a map, on a piece of paper, they're going to intersect at various points, and the trajectories that you get for the various experiments will follow those lines. And so last time I showed you this way of writing things up. So when you were not happy with the fact that the coordinates were increasing left and right, we had this. And if you now include the remaining lines, you have just another pass. So you have, before we had this pass, and it was doing like this, and now we have also this possible pass, or this possible pass for the viscous outer fluid. So it's the same thing as before, except that now we've included all of the mechanical factors. So now it's really hard to read because all of those lines, all of those points are on top of one another. But if you zoom in, you see, for instance, in the case where you have mostly inertial fluids, so low Unsorg numbers, you can see that some experiments go on one of the paths. So the Unsorg number, the Unsorg point is here. You can have either the case of going 1/2, so following the Rayleigh's regime, and then meeting the other sets of data which follow the 2/3 regime. And I've been asked, I don't remember who asked me this, but you have this mesh now. You have this sort of patch of space and time, and that has those sort of highways that are those regimes that are connected to one another by the dimensions of the mechanical factors. And the thing is that what dimensional analysis tells you is that if you observe dynamics that are due to these mechanical factors, they should follow those lines, but they don't tell you which line necessarily, which path is going to be taken. And this is a completely an open subject, is that in some cases, I like this experiment, for instance, by Eddy. He looked at coalescence of droplets that were either spread on the substrate or not. I mean, basically, depending on the wetting condition between the droplets and the substrate, he saw cases where the dynamics followed this path or the dynamics followed this path. So in this particular context, for the droplet coalescence on the substrate, there is some understanding as what are the parameters, in this case the contact angle, that are going to lead you on one side or on another side of this chart. But in most cases, it's still unknown what the reason for this. Okay, so I'm going to end by saying that you can find a bunch of stuff that I said plus more on how to use this table in a review that we did with Mathieu and Vivek, that is online and that you can find for free. But more importantly, I saw right when I arrived here, I saw the board, the blackboard outside, and I think that it's really cool. And so I think that I'm done with the lectures. I'm lucky. It's the third day. I'm done with the lectures, but I'll be happy to have discussion with you at any point during this week and the next one. And if we can eventually use this blackboard, that would be nice.